Welcome back. We're going to look at the nuclear chemistry section and radioactivity. This is something we didn't really talk about too much in class, so we'll go through the highlights right here. There's very little that you actually need to remember from this. Long story short, radioactivity is the decay of an unstable nucleus, okay, hence the name nuclear chemistry. Isotopes that contain unstable nuclei are called radioisotopes, and when we looked at the structure of the periodic table, you saw that most elements past 92, the transuranic elements, are radioactive. So just a quick refresher, uranium is the last naturally occurring element on the periodic table, element 92. So elements 93 through 118 are radioactive. There are a few, like technetium on the periodic table, which are also radioactive even though they're not transuranic. But general rule of thumb, transuranics are your radioactives. They're also the biggest, heaviest nuclei on the periodic table. When you undergo nuclear decay, you do what's called transmutation into smaller elements, and they emit energy. Basically, just think of it in terms of a large nucleus that you begin with is unstable, so think of it as shaking itself apart because it's got too many or too few neutrons, and so it will undergo a decay process whereby it makes a smaller nucleus or multiple smaller nuclei, and it can spit out a particle and some energy. So let's say this is uranium, and this one might be thorium. In which case, this is something called an alpha particle, and I'll go through that in one moment. The three forms of radiation are alpha, beta, and gamma. Now, these are the three ways that things can decay, and you can think of them in a simple breakdown. Alpha, beta, gamma. These two are particles. This one's just a wave, an electromagnetic wave. Very high energy light. Alpha particles are actually the nuclei of helium atoms. So they have a mass of 4 and a charge of +2 because they have 2 protons inside of them. No electrons though, so it's not a neutral atom. Beta particles are electrons that get ejected, mass of nothing, but a charge of -1 because it's an electron. And gamma, because it's just EM radiation or light, has no charge and no mass. When we're talking about these types of radiation, alpha will be stopped by something like a sheet of paper or your skin. So these are only dangerous if you swallow them or ingest them in some way. Beta particles, because they're smaller and less charged, will penetrate further, but a centimeter or so of a thin sheet of metal, like aluminum foil, that will stop that. Again, these are only pretty much dangerous if you ingest them. It'll penetrate a few centimeters of your skin, maybe reach the outer layer of muscles, but it won't actually reach your internal organs because it has charge, so it'll interact with matter pretty readily. Gamma radiation, on the other hand, does not get stopped because of charge or mass because it doesn't have it. And so to stop gamma radiation, it will penetrate the furthest. You actually need several centimeters of lead. Okay, lead will stop gamma radiation by absorbing it through the block, so if it makes it halfway through, it doesn't actually come out the other side. Or several feet or meters of concrete. Again, the gamma radiation will go in some extent, but then it will get stopped by the time it gets to the end. It's most penetrating because it has the most energy, has no charge or mass, so it can just blast right through matter without interacting very strongly with it. And that video we watched on nuclear radiation, this is what's considered, or these are what are considered ionizing radiation. So they are damaging to the body because they can knock electrons off of atoms in your cell. Alright, moving along, alpha particles are called helium atoms because it's the nucleus of a helium atom. Pretty self-explanatory. Background radiation, the stuff that's literally in the background of the world, is not harmful because it's always there. Think of radiation as being good and evil. There are very low energy kinds of radiation, like visible light, that surround us all the time. It doesn't harm us. Infrared is heat. That doesn't harm us unless there's a lot of it, and then you'll catch on fire. And anything lower than that, the only way it can harm you, like microwaves for example, is by actually heating your body until it combusts or melts in various places. It won't give you cancer because it's not ionizing. It's not strong enough. And if you want a quick refresher on that, just remember to go to the nuclear chemistry videos already up on Canvas and watch the last video again, although all of them I would recommend. You can detect radiation with Geiger counters, scintillation detectors, or there's also something called a film badge, but Geiger counters are the most common ones. Half-lives elapsed is just determined by the percent of the original substance remaining. Again, watch the video on Canvas if you need to refresh yourself on half-life, but long story short, let me zoom out here. If you start with 100% of a sample, after one half-life, you drop to 50%. Obviously this isn't to scale, but I'll just write the numbers. And after a second half-life, you will drop down to 25%. After a third half-life, you will drop down to 12.5%. And then fourth half-life, 6.25%. You get the idea. Every single time we subtract half, or we divide it by 2, hence the name, half-life. If this were in grams instead of percent, assuming I started with 100 grams, after one half-life I would have 50, 2 I would have 25, 3 I would have 12.5, and 4 I would have 6.25 grams. And whatever it was producing would fill in the bar in the other direction. So to begin with, I have 0% of whatever it produces. If I add on a bar on top of this to represent what's being produced, after one half-life, it's 50% original, 50% new stuff. After two half-lives, the original substance has dropped to 25%, the new substance has increased to 75%. Notice it's always filling it in to add up to 100%. So this bar represents 87.5%. And the final bar represents 93.75%. Whoops. Tried to write that as a fraction there. There we go. And of course at the beginning, no new product is formed. So as the original sample decays exponentially, the new sample grows exponentially. Again, this drawing, definitely not to scale, but you get the idea. Which is how carbon-14 is used to date artifacts, because we know the half-life of carbon-14, so we just have to measure how much carbon-14 is left compared to how much of its product isotope there is, so nitrogen-14 in that case. So if these black bars represent carbon-14, assuming it's very recent, it's all carbon-14. Assuming it's gone through one half-life, which is about 6,000-ish years. Then it will have 50% carbon-14, 50% nitrogen-14. If it goes through a second half-life, so it would be again about 12,000-ish years, you would have 25% of the carbon-14 remaining, and 75% of that nitrogen-14 has been produced there. So just by measuring that ratio, we can fill it in on the graph wherever it happens to be and say, oh, it's gone through 3 half-lives, so 1, 2, 3, and a half-life, let's say, is 6,000 years. 6,000 times 3 is 18,000 years. So it was 18,000 years old. Simple as that. All right, moving right along. Nuclear fusion and fission. Again, I recommend watching the video on Canvas if you need to refresh yourself. But fusion, or fusing, is creating bigger things from smaller things, and it releases energy. Fission is splitting larger things into smaller things, but it also releases energy. Fission is the one that we can control quite readily. Fusion is the one that we don't really know how to control yet because the temperatures and pressures required are enormous. The record is just a second or two of controlled fusion before the reactor has to shut down, so it's still decades away from being practical. Moving along, chain reactions can be dangerous if they happen outside of a nuclear reactor because they go out of control, and it's an out-of-control energy release. It's a runaway reaction, basically. Think atom bomb. Nuclear power plants are deliberately designed to slow the chain reaction down, which is how we control the power released. If you remove those control rods, it would go out of control and it would melt down. Not explode, because the purity of the material is nowhere near atom bomb quality, but it will get hot enough to melt down the core and make the reactor unusable. All right, a couple of simple math questions here. Half-life of cobalt-60 is 5.26 years. How many half-lives have passed in 10.52 years? I simply divide the time elapsed by the half-life to find that 2 half-lives have passed. 12.5% of a radioactive sample is left. How many half-lives have passed? Well, 12.5%, working backwards, double it. 25%, double that. 50%, double that. I'm back to 100. How many times I doubled is how many half-lives. 3 times 3 half-lives. All right, the balanced equation for the alpha decay of thorium-232. Sounds complicated, boils down to conservation of mass, and all you have to do is subtract and use a periodic table. Alpha, 4/2 helium. So thorium-232, I look on the periodic table to get the bottom number, and I find that thorium is atomic number 90. This was isotope notation from the beginning of the year. It decays, so this is like a decomposition reaction, except it's not chemical, it's nuclear, and it produces an alpha particle, because it's alpha decay, so 4/2 He. Well, I can't destroy mass, so 232 minus 4 gives me 228 as my new mass. 90 minus 2 gives me 88 for my new atomic number. And because this is a new atomic number, I can use the periodic table and look for element 88, which happens to be right here. It's the last alkaline earth metal. It is radium. Okay? So I write the symbol Ra, and then I'm finished. A quirky kind of decay, beta decay, is where it actually spits out an electron. And the weird thing about this is when you spit out an electron, one of your neutrons turns into a proton. So the mass does not change, but the atomic number actually winds up going up by 1. So carbon-14 decays by emitting a beta particle and turning into nitrogen-14, because -1 plus 7 equals 6. Alright, tune in for the next video for physics.